Resistance. If we take a simple series circuit containing a cell, an ammeter in series, and a fixed resistor with a voltmeter in parallel with it, we can measure the current through and the potential difference across the resistor. By then changing the number of cells to 2, 3, and more, we can increase the potential difference across the resistor. As we do that, the current will also increase. If we now plot a graph with current on the y-axis against potential difference on the x-axis, as long as the temperature of the resistor remains constant, we should get something like this, a straight line through the origin. This shows us that current is directly proportional to potential difference, meaning if we double the potential difference, we will double the current, treble the potential difference, treble the current, and so on. This relationship is known as Ohm's law. It applies to metals as long as the temperature is constant. But as we'll see later, there are many things that do not obey Ohm's law. We can write this statement in shorthand as I alpha V, where I is the symbol for current, alpha means is directly proportional to, and V for the potential difference or voltage. We can from this write that the voltage divided by the current will equal a constant, and this constant is the resistance of the circuit in ohms. So we can define resistance as equal to the potential difference across a component divided by the current flowing through it. In symbols, R for resistance is equal to V for potential difference divided by I for current. Potential difference is measured in volts, symbol capital V. Current is measured in amperes, symbol capital A, often abbreviated to amps. And resistance is measured in ohms, given the symbol of the Greek letter omega. As I said a moment ago, a metal wire at a constant temperature does obey Ohm's law, and its resistance can be found from the gradient of a graph of potential difference against current. Notice that our previous graph had current on the y-axis and potential difference on the x-axis. The gradient of that graph would have been the inverse of the gradient. But if we do plot potential difference against current like this, the gradient gives us the resistance, but only for a component obeying Ohm's law. The filament in a filament lamp certainly does not stay at a constant temperature, and so if we plot a graph of current against potential difference for a filament lamp, we get a trace something like this. If we consider a certain rise in potential difference here, it produces this rise in current. Looking at the effect of the same rise in potential difference here, we find it leads to a much smaller rise in current. To find the resistance from a graph like this, we don't simply find the gradient. What we need to do is get a value for potential difference and a value for current, and then the resistance in ohms is equal to the potential difference divided by the current. Let's pick two values for the same graph. Here I've put numbers on the axes. First, for 2 volts, we find a current of 2.4 amps. And so the resistance is potential difference divided by current, in this case 2 divided by 2.4, giving a resistance of 0.83 ohms. From 12 volts, we get a current here of just over 8 amps. So in this case, resistance is potential difference divided by current. 12 divided by 8.2 in this case, the resistance has gone up to 1.46 ohms. So the resistance of the filament lamp has increased as the temperature has risen. A negative temperature coefficient thermistor gives a graph of current against potential difference, something like this. Again, finding the values of potential difference and current at 2 volts, we get that the resistance is equal to potential difference divided by current, in this case 2 divided by 0.5, 4 ohms. From 12 volts, we then find that resistance is potential difference divided by current, in this case 12 divided by 6, giving a resistance of 2 ohms. So in this case, with the negative temperature coefficient thermistor, the resistance has dropped. In both the filament lamp and the thermistor, it is the current which has led to a rise in temperature which has caused the change in resistance. So how can a rise in temperature cause a filament lamp to increase its resistance and a thermistor decrease? Well, to understand that, we need to look at what is happening as current flows through a component. Here we'll look at electricity conduction in metals. Metals have a plentiful supply of free electrons surrounding a lattice of positive ions. An electron will want to travel from the negative side towards the positive side and might follow a path something like this. The electrons collide with the positive ions in the lattice, and this is the cause of resistance. These collisions hinder the path of the electrons. As the temperature rises, due to collisions of the electrons with the positive ions, the vibrations increase. This will lead to more collisions and so more resistance. This is what happens in the filament of a lamp, the filament being a piece of wire. So why is the thermistor so different? Well, the thermistor is made mainly of silicon, and here we have a model of pure silicon, the blue circles here representing the bonding electrons. The electrons are held tightly in pure silicon, so it is a poor conductor. But if we add an impurity, in this case phosphorus, this adds an extra electron, which becomes a free electron. We call this doping. This silicon has been doped with phosphorus. So we get free electrons. These can then conduct. As the temperature of the silicon or the doped silicon rises, the vibration of the positive ions will increase, just as it did in the filament. This will lead to more collisions, and so make it harder for any one electron to move through the material. But the rise in temperature and the vibrations frees up more electrons, meaning more charge carriers are available. In a negative temperature coefficient thermistor, the second effect of freeing up electrons is much greater than the first effect of causing more resistance for any one electron. Thus, as the temperature of an NTC thermistor rises, its resistance falls.